Okay, I'm back, and now we're going to talk about the forces that act inside the nucleus of the atom. So these are the final two fundamental forces of nature. So if you recall, in unit number 1, we talked about gravity, and so gravity is the cosmic force. It's the thing that holds the universe together. It holds clusters of galaxies together. It holds galaxies together. It holds stars together. It holds planets together. So on very, very large scales, gravity is the fundamental force that operates. Then we also talked about on the atomic level, you're going to have the electromagnetic force. So the EM force. And so that's what's holding this pen together. So the atoms that make up the plastic are being held together by basically the force of electricity. And so we're going to call that the electromagnetic force. Now we want to talk about, though, what is it that's holding the nucleus together? So those protons and those neutrons. It's not electricity. Because think about it. What's inside the nucleus? Protons and neutrons. So imagine having all of these protons together. They don't like each other. Like charges repel. So if it was up to the electromagnetic force, the nucleus would blow itself apart. So there must be a stronger force than the force of electromagnetism inside the nucleus, and so that's why they call it the strong nuclear force. So the strong nuclear force is what's going to bind protons and neutrons together inside the nucleus. Now later in Unit 4, we're going to find out that inside protons are these things that are going to be called quarks. And so this strong nuclear force, what it really does is it's holding the quarks together to make protons and neutrons, and then again holding those together as well to make the nucleus. Now the weak nuclear force it's a little bit strange, but imagine that you had a nucleus that had too many protons. Now normally a nucleus likes to have roughly equal numbers of protons and neutrons. Now that's not quite true. So it turns out that the bigger that the nucleus gets, it likes to have more neutrons in there as well. But let's just say, for the sake of argument, that a typical nucleus is going to like to have equal numbers of protons and neutrons. Now let's pretend that this particular nucleus, though, has too many protons. So let me just add some more protons onto this nucleus. Okay, now this would be an unstable nucleus because that nucleus, those protons, they don't like each other and they would be pushing against each other, and that's why this nucleus would be unstable and it would tend to blow itself apart. So nature has a way of changing these protons, or at least a few of these protons, into neutrons. So that proton just changed into a neutron. And so now there's less protons that are pushing against each other. And so that helps to make this nucleus more stable. So here we've got this little equation here that shows a proton, which has a positive charge, is changing, that's what the arrow means, is changing into a neutron, which has 0 charge. And there's a rule in nature that says no can do. You can't just make charges out of thin air. So what we have to do is have another charge has to appear in order to balance that neutron. And so we're going to call it the beta particle. And do you notice what's the charge on that beta particle, the B-looking thing? So it's a positive charge. So we start with a positive charge, the proton, and then after it changes into a neutron, we've got this other extra little particle that has a positive charge. I know it seems like magic, but that's what actually happens in nature. And then there's another little particle that is emitted, and it's that V-shaped thing, but it's not an actual V, it's a nu. And so it's called a neutron. So the symbol is nu, and it's called the neutron, and it's a teeny tiny little particle that also has to be emitted in order to account for spin. Because the proton, let's say, was spinning like this, and then it turns into a neutron, which is spinning in the same direction, but the beta particle also has spin, so we need to have one more particle that will spin in the opposite direction and will balance out that beta particle. It's complicated. So the point is, we needed one extra particle to come out. Now, I'm not going to be too concerned about the neutrinos, but later in Unit 4, when we talk about the origin of the universe, we're going to talk about a substance called dark matter. And one of the theories as to what dark matter could possibly be is neutrinos. And so we'll talk about that later. So for all I need for you to see is that a proton can be changed into a neutron. That's what I want you to get. Now, if a nucleus has too many neutrons, that's also bad. And that particular nucleus would be unstable. So a neutron can change into a proton. And it would also give off a beta particle, but this time it's called the beta minus particle. So do you notice that the proton's positive, the beta minus is negative, plus and a negative means 0, and the neutron has 0 charge. So it helps to balance out the charge on it, and then it also gives off another neutrino. Well, they found out later that the beta minus particle is just really the electron. But they had already named it the beta minus particle, so they decided not to change the name of it. But the beta minus is just an electron. So what is the beta plus particle then? Well, it would be the same size as the electron, but it would have positive charge. And so we call it the positron. And so the electron and the positron are matter and antimatter. And we'll get into that in unit number 4. So the point is that the process by which a proton can be changed into a neutron, or a neutron can be changed into a proton, is mediated by the weak nuclear force. That's what its job is. Okay, so now you know the names of the 4 fundamental forces that control the universe. So what's the first one? Begins with a G. Gravity. Okay, it's the cosmic one. It's the big one. Okay, what's the thing that's holding the atoms together inside the plastic of this? Okay, that's the electromagnetic force. And now we've got 2 more forces that operate inside the nucleus, the strong nuclear force and the weak nuclear force. Okay, we're going to take a break, and when we come back, we're going to start to talk about how does the nucleus generate energy.